Well, welcome back to our course, Computer Organization and Architectures. For this lecture, we're going to be talking about reduced instruction set computers. And so just to give a context here, this is the second in terms of 4 lectures that we're going to be focusing on the central processing unit. And so we have talked about the ARM processor before. We've had a little bit of an introduction to what is going on there. And so this will be sort of a general, more high-level perspective of talking about that. And so I think this will be useful, and you'll see here some of the historical types of processors that have been part of the RISC family over time. So here's a listing of the topics that we'll cover. We'll just go through this quickly, and then after we're done with the details, we'll come back to the same chart to review this summary. And so first of all, we'll talk about the instruction execution characteristics for the RISC, reduced instruction set computing. And CISC is the complex instruction set computing. So keep that in mind that we have the RISC and the CISC. We'll be talking about the use of large register files. We'll talk about the reduced instruction set architecture and think about the CISC versus the RISC characteristics. Then we'll get into some specific type of processing and first of all, in general, talking about the RISC pipelining. We'll talk about the MIPS R4000, and we will be using an emulator, a Mars MIP emulator, for some of our hands-on work that we'll be doing in class. We'll talk about the Spark architecture. This was developed by Sun Microsystems. And then we'll talk about the processor organization for pipelining, and then thinking about the CISC, RISC, and contemporary systems as things are going on, at least at the time of the publishing, for the resources that we're using for this course, as textbooks, lecture notes, etc. So here is the first part of table 17.1. It shows the characteristics of CISC, RISC, and superscalar processors, and we'll get into superscalar as we progress through this lecture. But first of all, let's talk about the complex instruction set computer, the CISC. So we have the IBM 370, the VAX, and then we have the Intel line with the x86, and we're focusing here on the 8486. So we can see that the number of instructions are larger as compared to what we have for the reduced instruction set. For the Spark, the Sun Microsystem product, they had a 69 versus the MIPS R4000 had 94. And so we have that as a comparison. So this is the first of 2 charts just to give a general comparison. You can look over these and pause the video if you want to be thinking about that in a little bit more detail. Then moving on, these are some later developments. We have the PowerPC, which was still, here's an example of the superscalar type of processors. We have the UltraSpark, which is still part of the Sun Microsystem family, and then the eventually open source, the Spark design. And then we have the MIPS R10000. So thus we see the CISC, the RISC, and the superscalar processors that are worth noting as we talk about the material that we'll be discussing in this course. So one of the most valuable forms of evolution associated with computers is that of programming languages. As the cost of hardware has dropped, the relative cost of software has risen. Along with that, a chronic shortage of programmers has driven up software costs in absolute terms. Thus, the major cost in the life cycle of a system is software, not hardware. Maybe not intuitive, but that's the case. Adding to the cost and to the inconvenience is the element of unreliability. It is common for programmers, both system and application, to continue to exhibit new bugs after years of operation. The response from researchers in industry has been to develop ever more powerful and complex higher level languages These high-level languages, or HLLs, one, allow the programmer to express algorithms more concisely. Two, allow the compiler to take care of details that are not important in the programmer's expression of algorithms. And three, often support naturally the use of structured programming and or object-oriented design. Alas, the solution gave rise to the to a perceived problem known as the semantic gap. The differences between the operation provided in the high-level languages and those provided in computer architectures. Symptoms of this gap are alleged to include execution inefficiency, excessive machine program size, and compiler complexities. Designers responded with architectures intended to close this gap. Key features include large instruction sets, dozens of addressing modes, and various high-level language statements implemented in hardware. An example of the case of the latter is the case machine instruction on the VAX. Such complex instruction sets are intended to ease the task of the compiler writer, improve execution efficiency because complex sequences of operations can be implemented in microcode. So microcode is just a step down below assembly language, just to give you a perspective. Provide support for even more complex and sophisticated high-level languages. Meanwhile, a number of studies have been done over the years to determine the characteristics and patterns of execution of machine instructions generated from high-level language programs. The results of these studies inspired some researchers to look for a different approach, namely to make the architecture that support the high-level language simpler rather than more complex. To understand the line of reasoning of the risk advocates, we begin with a brief review of instruction execution characteristics. The aspects of the computation of interest are as follows. Operations performed. These determine the function to be performed by the processor and its interactions with memory. Operands used. The type of operands and the frequency of their use determine the memory organization for storing them and the addressing modes for accessing them. And then executing sequences, this determines the control and pipelining organizations. So in the remainder of what we'll talk about in this subsection, we'll summarize the result of a number of studies of high-level language programs. All of the results are based on dynamic measurements. That is, measurements are collected by executing the program and collecting the number of times some features has appeared or a particular property has held true. In contrast, static measurements merely perform these counts on the source text of a program. They give no useful information on performance because they are not weighed relative to the number of times each statement is executed. Okay, here we're showing the weighted relative dynamic features of high-level language operations. This is based on reference from our text. A variety of studies have been made to analyze the behavior of high-level language programs with the following general conclusions. There is quite good agreement in the results of the mixture of assembly language, a mixture of language and applications. Assignment statements predominate, suggesting that the simple movement of data is of higher importance. There is also a preponderance of conditional statements, that is, if and loop type of statements. These statements are implemented in machine language with some sort of compare and branch instruction. This suggests that the sequence control mechanism of the instruction set is important. These results are instructive to the machine instruction set designer, indicating which types of statements occur most often and therefore should be supported in an optimal fashion. However, these results do not reveal which statements use the most time in the execution of a typical program. That is, we want to answer the question, given a compiled machine language program, which statement in the source language caused the execution of the most machine language instructions, and what is the execution time of these instructions? To get at the underlying phenomena, one of the references, Patterson and Sequin, analyze a set of measurements taken from compilers and programs for typesetting, computer-aided design or CAD, sorting, and file comparison. The programming language C and Pascal compiled on the VAX, PDP-11, and Motorola 68000 to determine the average number of machine instructions and memory references per statement type. The second and third columns in table 17.2, which we're showing, illustrates the relative frequencies of occurrences of various high-level language statements in a variety of programs. The data were obtained by observing the occurrences in running programs rather than just the number of times that the statement occurred in source code. Hence, these metrics captures dynamic behavior. To obtain the data in columns 4 and 5, the machine instruction weighted, each value in the second and third columns is multiplied by the number of machine instructions produced by the compiler. These results are then normalized so that the columns 4 and 5 show the relative frequency of the occurrence weighted by the number of machine instructions per high-level language statement. Similarly, the 6th and 7th column are obtained by multiplying the frequency of occurrences of each statement type by the relative number of memory references caused by each statement. The data in column 4 through 7 provides surrogate measurements of the actual time spent executing the various statement types. The results suggest that the procedure call and return is the most time-consuming operation in a typical high-level language program. The results should be clear on the significance of table 17.2. The table indicates the relative performance impact of the various statement types in high-level language when the high-level language is compiled for a typical contemporary instruction set architecture. Some other architectures could conceivably produce different results. However, the study produces results that are representative for contemporary complex instruction set computers or CISC architectures. Thus, they can provide guidance to those looking for more efficient ways to support high-level languages. So continuing on, thinking in terms of dynamic percentage of operands, much less work has been done on the occurrence of the types of operands. Despite the importance of this topic, there are several aspects that are significant. The Patterson study, which was already referenced, also looked at the dynamic frequency of occurrences of classes of variables. We're showing that in table 17.3 that is on the display now. The results consistent between Pascal and C programs show the most references are to the simple scalar variables. Further, much more than 80% of the scalars were local, that is to the procedure variables, that is to the procedure. So we're talking about local variables. In addition, each reference to an array or a structure requires a reference to an index or pointer, which again is usually a local scalar. Thus, there is a preponderance of references to scalars, and these are highly localized. Patterson's study examined the dynamic behavior of high-level language programs independent of the underlying architecture. As discussed before, it is necessary to deal with actual architectures to examine program behavior more deeply. One study examined DEC 10 instructions dynamically and found that each instruction on the average references 0.5 operand in memory and 1.4 registers. Similar results are reported in other studies for C and Pascal and Fortran programs on CS360 PDP-11 and VAX, so an IBM PDP-11 and a VAX type of computer. Of course, these figures depend highly on both the architecture and the compiler, but they do illustrate the frequency of operand accessing. These later studies suggest the importance of an architecture that lends itself to fast operand accessing because this operation is performed so frequently. The Patterson study suggests that a prime candidate for optimization is the mechanism for storing and accessing local scalar variables. Though I think you're seeing from our textbook and the things that they're quoting with studies, they're trying to leverage research, published studies and stuff like that to give some insight into the direction in which computer architecture has evolved in terms of optimization, and at times may not be extremely obvious, but through trial and error and actual demonstration and experimentation, they found results that are across multiple points in the computing environment, how it can improve performance. Okay, well, let's talk about procedure arguments and local scalar variables. We have seen that procedure calls and returns are an important aspects of high-level language programs. The evidence, so stuff we showed in table 17.2, suggests that there are the most time-consuming operations in compiled high-level language programs. Thus, it will be profitable to consider ways of implementing these operations efficiently. Two aspects are significant: the number of parameters and variables that a procedure deals with and the depth of nesting. A study by Tannenbaum has a nice textbooks on operating systems, if you haven't seen it, found that 98% of dynamically called procedures were passed fewer than 6 arguments, and that 92% of them were fewer than 6 local scalar variables. Similar results were reported by the Berkeley RISC team, as shown in table 17.4, which we're showing here. These results show that the number of words required per procedure activation is not large. The study reported earlier indicate that a high proportion of operand references is a local scalar variable. These studies show that those references are in fact confined to relatively few variables. Same Berkeley group also looked at the pattern of procedures, calls, and returns in high-level language programs. They found it rare to have a long uninterrupted sequence of procedure calls followed by the corresponding sequence of returns. Rather, they found that a program remains confined to a rather narrow window of procedures invocation depth. These results reinforce the conclusion that operand references are highly localized. A number of groups have looked at results such as those just reported and have concluded that the attempt to make the instruction set architecture close to high-level languages is not the most effective design strategy. Rather, the high-level languages can best be supported by optimized performance of the most time-consuming features of typical high-level language programs. Generalizing from the work of a number of researchers, 3 elements emerged that by and large characterize RISC architecture. First, use a large number of registers or use a compiler to optimize register usage. This is intended to optimize operand referencing. The studies just discussed show that there are several references per high-level language statement, and that there is a high proportion of move, that is assignment statements. This, coupled with the locality and predominance of scalar references, suggests that performance can be improved by reducing memory references at the expense of more register references. Because of the locality of these references, an expanded register set seems practical. Second, careful attention needs to be paid to the design of instruction pipelines. Because of the high proportion of conditional branch and procedure call instructions, a straightforward instruction pipeline will be inefficient. This manifests itself as a high proportion of instructions that are prefetched but never executed. Finally, an instruction set consisting of high performance primitives is indicated. Instructions should have predictable costs, that is measured in execution time and code size, and increasing in energy dissipation, and be consistent with a high performance implementation which harmonizes with predictable execution time cost. The reason that register storage is indicated is that it is is the fastest available storage device, faster than both main memory and the cache system. The register file is physically small on the same chip as the arithmetic logic unit, and control unit and employs much shorter addresses than addresses for cache and memory. Thus, a strategy is needed that will allow the most frequently accessed operands to keep in register, to be kept in registers and to minimize register memory operations. Two basic approaches are possible, one based on software and the other on hardware. The software approach is to rely on the compiler to maximize register usage. The compiler will attempt to assign registers to those variables that will be used the most in a given time period. This approach requires the use of a sophisticated program analysis algorithm. The hardware approach is simpler to use more register so that the variables can be held in registers for a longer period of time. So in this section, we will discuss the hardware approach. The approach has been pioneered by the Berkeley RISC group, was used in the first commercial RISC products, the Pyramid, and is currently used in the popular Spark architecture. And so Spark is the line of processors that Sun Microsystem, which now has been bought by Oracle, uses. On the face of it, the use of a large set of registers should decrease the need to access memory. The design task is to organize the registers in such a fashion that the goal is realized. Because most operand references are to local scalars, the obvious approach is to store these in registers with perhaps a few registers reserved for global variables. The problem is that each definition of local changes with each procedure call and return operations that occur frequently. On every call, local variables must be saved from the registers into memory so that the registers can be reused by the call procedure. Furthermore, parameters must be passed. On return, the variables of the calling procedure must be restored, that is loaded back into registers, and results must be passed back to the calling procedures. The solution is based on two other results reported in section 17.1. First, a typical procedure employs only a few passed parameters and local variables. That's something that we saw in table 17.4. And second, the depth of procedure activation fluctuates with relatively narrow range. To exploit these properties, multiple small sets of registers are used, each assigned to different procedures. A procedure call automatically switches the procedure to use a different fixed size window of registers rather than saving registers in memory. Windows for adjacent procedures are overlapped to allow parameter passing. The concept is illustrated in figure 17.1, which we're showing here. At any time, only one window of registers is visible and is addressable as if it were the only set of registers. That is, addresses 0 through n-1. The window is divided into three fixed size areas. Parameter registers hold parameters passed down from the procedure that call the procedure and hold results to be passed back up. Local registers are used for local variables as assigned by the compiler. Temporary registers are used to exchange parameters and results with the next lower level, that is a procedure called by current procedure. The temporary registers at one level are physically the same as the parameter registers in the next lower level. It's useful to state again, the temporary registers at one level are physically the same as the parameter registers at the next lower level. This overlap permits parameters to be passed without the actual movement of data. Keep in mind that except for the overlap, the registers at two different levels are physically distinct. That is, the parameters and local registers at level J are disjoint from the local and temporary registers at level J+1. To handle any possible patterns of calls and returns, the number of register windows would have to be unbounded. Instead, the register windows can be used to hold the few most recent procedure activations. Older activations must be saved in memory and later restored when the nesting depth decreases. Thus, the actual organization of the register file is a circular buffer of overlapping windows. Two notable examples of this approach are Sun's Spark architecture described in 17.7, and we'll get to that shortly, and the IA64 architecture used in Intel's Itanium processor. So the circular organization is shown in figure 17.2, which we're showing on the display now, which depicts a circular buffer of 6 windows. The buffer is filled to a depth of 4. A calls B, B calls C, C calls D, with procedure D active. The current window pointer, CWP, points to the window of the currently active procedure. Register references by a machine instruction are offset by the pointer to determine the actual physical register. The save window pointer, SWP, identifies the window most recently saved in memory. If procedure D now calls procedure E, arguments for E are placed in D's temporary register, that is the overlap between W3 and W4, and the CWP is advanced by 1 window. If procedure E then makes a call to procedure F, the call cannot be made with the current status of the buffer. This is because F's window overlaps A's window. If A begins to load its temporary registers, preparing to in preparation to a call, it will overwrite the parameter register of A, that is AN. So A.N. Thus, when CWP is incremented in modulo 6, is incremented, and we're using the modulo operator, so incremented modulo 6, so that it becomes equal to SWP, an interrupt occurs and A's window is saved. Only the first 2 portions, that is A.N and A.LOC, need to be saved. Then the SWP is incremented and the call to F proceeds. A similar interrupt can occur on return. For example, subsequent to the activation of F, when B returns to A, CWP is decremented and becomes equal to SWP. This causes an interrupt that results in the restoration of A's window. From the proceeding, it can be seen that N window register file can hold only N-1 procedure activations. The value of N need not be large, as in the textbook, it refers to one of the studies pointing this out. One study found with 8 windows, a save or restore is needed on only 1% of the calls or returns. The Berkeley RISC computers use 8 windows of 16 registers each. The Pyramid computer employs 16 windows of 32 registers each. So there's a lot of things I can mention, but I'll just take 1 or 2 things here. And so we have a circular buffer. So some of you who have looked at data structures, perhaps you got exposed to a circular buffer. I mentioned modulo 6, and so we have F, so A, B, C, D, and E, and F. We have 6 states, and so that's why we're talking about modulo 6 here. And so we can either go save or restore, so we can twirl in one direction or another, call or return. And so we're keeping things readily available, way we have things there. Well, next, let's talk about global variables. Variables, this window, the window scheme for just described, provides an efficient organization for storing local scalar variables in registers. However, this scheme does not address the need to store global variables, those accessed by 2 or more, by more than 1 procedure. 2 options should suggest themselves. First, variables described as global variables in high-level language can be assigned memory locations by the computer, by the compiler, and all machine instructions that reference those variables will use memory reference operands. This is straightforward from both a hardware and software, that is software compiler point of view. However, for frequently accessed global variables, the scheme is inefficient. An alternative is to incorporate a set of global registers in the processor. These registers would be fixed in number and available to all procedures. A unified numbering scheme must be used to simplify the instruction format. For example, references to registers 0 through 7 could refer to unique global registers, and references to registers 8 through 31 could be offset to refer to physical registers in the current window. There is an increased hardware burden to accommodate the split in register addressing. In addition, the linker must decide which global variables should be assigned to registers. The register file organized into windows acts as a small, fast buffer for holding a subset of variables that are likely to be used the most heavily. From this point of view, the register file acts much like a cache memory, although a much faster memory. The question therefore arises as to whether it would be simpler and better to use a cache in a small traditional register file. Table 17.5 compares characteristics of the two approaches. The window-based register file holds all the variable scalar variables, except in the rare case of a window overflow of the most recent n-1 procedure activations. The cache holds a selection of recently used scalar variables. The register file should save time because all local scalar variables are retained. On the other hand, the cache may make more efficient use of space because it is reacting to the situation dynamically. Furthermore, cache generally treat all memory references alike, including instructions and other types of data. Thus, saving in these other areas are possible with a cache and not a register file. A register file may make inefficient use of space because not all procedures will need the full window space allotted to them. On the other hand, the cache suffers from another sort of inefficiency. Data are read into the cache in blocks, whereas a register file contains only those variables in use. The cache reads in a block of data, some or much of which will not be used. The cache is capable of handling global as well as local variables. There are usually many global scalars, but only a few of them are heavily used. A cache will dynamically discover these variables and hold them. If the window-based register file is supplemented with global registers, it too can hold some global scalars. However, when program modules are separately compiled, it is impossible for the compiler to assign global values to registers. The linker must perform this task. With the register file, the movement of data between registers and memory is determined by the procedure nesting depth. Because this depth usually fluctuates within a narrow range, the use of memory is relatively infrequent. Most cache memories are set associative with a small set size. Thus, there is a danger that other data or instructions will compete for cache residency. Based on the discussion so far, the choice between a large window-based register file and a cache is not clear-cut. There is one characteristic, however, in which the register approach is clearly superior than and which suggests that a cache-based system will be noticeably slower. The distinction shows up in the amount of addressing overhead experienced by the two approaches. Figure 17.3 illustrates the difference. To reference a local scalar in a window-based register file, a virtual register number and a window number are used. These can pass through a relatively simple decoder to select one of the physical registers. To reference a memory location in cache, a full width memory address must be generated. The complexity of the operation depends on the addressing mode. In a set associative cache, a portion of the address is used to read a number of words and tags equal to the set size. Another portion of the address is compared with the tags, and some of the words that were read is selected. Should be clear that even if the cache is as fast as the register file, the access time will be considerably longer. Thus, from the point of view of performance, the window-based register file is superior for local scalars. Further performance improvements could be achieved by the addition of the cache for instructions only. Well, let's continue on as we're thinking through some of these concepts. Now let's think about a graph coloring approach. So hopefully some of these pictures, tables, background information is giving you some context. The essence of the optimization task is to decide which quantities are to be assigned to registers at any given point in the program. The technique most commonly used in RISC compilers is known as graph coloring, which is a technique borrowed from the disciplines of topology. And so maybe you've heard that word, maybe you haven't, but getting into graph theory and tree structures and stuff like that. The graph coloring problem is this: given a graph consistent of nodes and edges, assign colors to nodes such that adjacent nodes have different colors, and do this in such a way as to minimize the number of different colors. The problem is adapted from the compiler problem in the following way. First, the program is analyzed to build a register interference graph. The node of the graphs are symbolic registers. If two symbolic registers are, quote, live during the same point program fragment, then they are joined by an edge to depict interference. An attempt is made to color the graph with n colors, where n is a number of registers. Nodes that share the same color can be assigned to the same register. If this process does not fully succeed, then those nodes that cannot be colored must be placed in memory, and loads and stores must be used to make space for the affected quantities when they are needed. Figure 17.4, which are showing here, is a simple example of the process. Assume a program with 6 symbolic registers to be compiled into 3 actual registers. So in figures 17.4a, it shows a time sequence of active use of each symbolic register. The dashed horizontal line indicates successive instruction executions. Figure 17.4b shows a register interference graph. Shading and crosshatching are used instead of colors. A possible coloring with 3 colors is indicated. Because symbolic registers A and D do not interfere, the compile can assign both of these to physical registers R1. Similarly, symbolic registers C and E can be assigned to registers R3. One symbolic register F is left uncolored and must be dealt with using loads and stores. In general, there is a trade-off between the use of large sets of registers and compiler-based register optimization. For example, one study reports that looked at modeling a RISC architecture with features similar to the Motorola 88,000 and the MIPS R2000. The researchers varied the number of registers from 16 to 128, and they considered both the use of the general purpose registers and register split between integer and floating point use. Their studies showed that with even simple register optimization, there is little benefit to the use of more than 64 registers. With reasonably sophisticated register optimization techniques, there is only marginal performance improvements with more than 32 registers. Finally, they noted that with a small number of registers, for example, 16, a machine with a shared register organization executes faster than one with a split organization. Similar conclusions can be drawn from another study, which reports that a primary concern was optimizing the use of small number of registers rather than compared with the use of large register sets with optimization efforts. Okay, so we've had some general considerations for how we can begin to think about optimizing the number of registers, and registers are better than cache. Cache is better than main memory. But now let's ask another question. Why CISC? Why would we want to be using a complex instruction set? We have noted the trend to richer instruction sets, and previous lectures we were talking about that, where users were asking for more and more ability to have surgical access and control. So this includes a larger number of instructions and more complex instructions. Two principal reasons have motivated this trend: a desire to simplify compilers and a desire to improve performance. Underlining both of these reasons was a shift to high-level languages on the part of programmers. Architecture attempts to design machines that provide better support for high-level languages. So people are not programming as much in assembly language would be another way of maybe giving a shorthand way of thinking about that. It is not the intent of this chapter to say that CISC designers took the wrong direction. Instead, because technology continues to evolve and because architectures exist along a spectrum rather than on two neat categories, a black and white assessment is unlikely ever to emerge. Thus, the comments that follow any simple means to point out some of the potential pitfalls in the CISC approach and to provide some understanding of the motivation of the risk adherence. The first of the reasons cited, compiler simplification, seems obvious, but it is not. The task of the computer writer is to build a compiler that generates good, that is fast and small. So these are the things that ultimately we need to think about. Of course, I would argue fast and small would be great, but it's not always worked that well, that in either having one or the other. So fast, small, and another possibility is fast and small. So sequence of machine instructions for high-level languages, that is, the compiler views individual high-level language statements in the context of surrounding high-level language statements. If there are machine instructions that resemble high-level language statements, this task is simplified. The reasoning has been disputed by some researchers. They have found that complex machine instructions are often hard to exploit because the compiler must find those cases that exactly fit the construct. So keep that in mind. You have all these extra operations, these commands, but you can't always use that. The task of optimizing the generated code to minimum code size, reduce instruction execution count, and enhance pipelining is more and more difficult with a complex instruction set. As evidence of this, studies cite earlier in this chapter indicate that most of the instruction is a compiled program or the relatively simple ones. The other major reason cited is the expectation that a CISC will yield smaller, faster programs. Let us examine both aspects of this assertion. The programs will be smaller and that they will execute faster. There are two advantages to the smaller programs. First, because the program takes up less memory, there is a savings in that resource. With memory today being so inexpensive, the potential advantage is no longer compelling. More important, smaller programs should improve performance, and this will happen in three ways. First, fewer instructions means fewer instruction bytes to be fetched. Second, in a paging improvement, smaller programs occupy fewer pages, reducing page fault errors. And third, more instructions can fit into the cache. The problem with the line of reasoning is that as far from certain that a CISC program will be smaller than a corresponding RISC program. In many cases, the CISC program expressed in symbolic machine language may be shorter, that is, fewer instructions, but the number of bits of memory occupied may be noticeably smaller. Table 17.6 shows the results for 3 studies that compared the size of compiled C programs on a variety of machines, including a RISC-1, which has a reduced instruction set architecture. Note that there is little or no savings using a CISC over a RISC. It is also interesting to note that a VAX, which has a much more complex instruction set than a PDP-11, achieved very little savings over the latter. These results were confirmed by IBM researchers, which found that the IBM 801, which is a RISC processor, produced code that was 0.9 times the size of the code on IBM 370. The study used a set of PL1 programs. There are several reasons for these rather surprising results. We have already noted that compilers on CISC tend to favor simpler instructions so that the conciseness of the complex instructions seldom come into play. Also, because of these important instructions on a CISC, longer opcodes are required, producing longer instructions. Finally, RISCs tend to emphasize register rather than memory references, and the former require fewer bits. An example of this last effect is discussed presently. So the expectation that a CISC will produce smaller programs with the attendant advantage may not be realized. The second motivating factor for increasing complex instruction sets was the instruction execution would be faster. Seems to make sense that a complex high-level language operation will execute more quickly as a single machine instruction rather than a series of more primitive instructions. However, because of the bias towards the use of those simpler instructions, this may not be so. The entire control unit must be made more complex, and or the microprogram control store must be made larger to accommodate a richer instruction set. Either factor increases the execution time of the simple instructions. In fact, some researchers have found that the speed up in the execution of complex instructions is due not so much to the power of the complex machine instruction as to their resonance in high-speed control store. In effect, the control store acts as an instruction cache. Thus, the hardware architecture is in the position of trying to determine which subroutines or functions will be used most frequently and assign those to the control store by implementing them in microcode. The results have been less than encouraging. On IBM 390 system, instructions such as translate and execute and extended precision floating point divide reside in high-speed storage, while the sequence involved in setting up procedure calls or initiating an interrupt handler are in slower main memory. Thus, it is far from clear that a trend to increasingly complex instruction sets is appropriate. This has led a number of groups to pursue the opposite path. So you can see there's give and take thinking between the CISC and the RISC architectures, and when one would be more preferable to another. It turns out that Apple recently changed its processor away from Intel to an ARM processor, having their own processor that they have control over. So it's now using a reduced instruction set. For Microsoft Windows, it now can operate on both an x86 architecture or in an ARM-based processor. They have for the Microsoft Surface that they have an agreement with a provider that provides that processor, Qualcomm. Okay, well, let's continue. Although a variety of different approaches to reduce instruction set architecture has been taken, certain characteristics are common to all of them. One instruction per cycle, register-to-register operation, simple addressing modes, and simple instruction formats. Here we provide a brief discussion of each of these characteristics. Specific examples are explored later in this chapter. The first characteristic list is that there is one machine instruction per machine cycle. a machine cycle is defined to be the time it takes to fetch one operand from registers, perform an ALU operation, and restore the results in a register. Thus, RISC machine instructions should be no more complicated and execute about as fast as micro instructions on a CISC machine. This is something that will be discussed in part 4, so keep that in mind as we move forward. With simple one-cycle instruction, there is little or no need for micro code. The machine instructions can be hardwired. Such instruction should execute faster than comparable machine instructions on other machines because it is not necessary to access a microprogram control store during instruction execution. The second characteristic is that most operations should be registered to register with only simple load and store operations accessing memory. This design feature simplifies the instruction set and therefore the control unit. For example, a RISC instruction set may include only one or two add instructions. For example, integer add and add with carry. The VAX had 25 different add instructions. Another benefit is that such an architecture encourages the optimization of register use so that frequently accessed operands remain in high-speed storage. A third characteristic is the use of the simple address modes. Almost all RISC instructions use simple register addressing. Several additional modes such as displacement and PC relative may be included. Another more complex mode can be synthesized in software from the simple ones. Again, this design feature simplifies the instruction set and the control unit. A final common characteristic is the use of simple instruction formats. Generally, only one of the few formats are used. Instruction length is fixed and aligned on word boundaries. Field locations, especially the opcode, are fixed. The design feature has a number of benefits. With fixed fields, opcode decoding and register operand accessing can occur simultaneously. Simplified formats simplify the control unit. Instruction fetching is optimized because word length units are fetched. Alignment on a word boundary also means that a single instruction does not cross page boundaries. Okay, for following on for characteristics of reduced instruction set characteristics, RISC. So taken together, these characteristics can be assessed to determine the potential performance benefits of a RISC approach. A certain amount of, quote, circumstantial evidence can be presented. First, more effective optimizing compilers can be developed. With more primitive instructions, there are more opportunities for moving functions out of loops, reorganizing code for efficiency, maximizing register utilization, and so forth. It is even possible to compute part of complex instructions at compile time. For example, the S390 move characters MVC instruction moves a string of characters from one location to another. Each time it executes, the move will depend on the length of the string, whether and in which direction the locations overlap, and what the alignment characteristics are. In most cases, these all will be known at compile time. Thus, the compiler would produce an optimized sequence of primitive instructions for the function. A second point already noted is that most instructions generated by a compiler are relatively simple anyway. It would seem reasonable that a control unit built specifically for those instructions and using little or no microcode could execute these faster than a comparable CISC. A third point relates to the use of instruction pipelining. RISC researchers feel that the instruction pipeline technique can be applied much more effectively with a reduced instruction set. We examine this point in some detail presently. A final and somewhat less significant point is that RISC processors are more responsive to interrupts because interrupts are checked between rather elementary operations. Architectures with complex instructions either restrict interrupts to instruction boundaries or must define specific interruptible points and implement mechanisms for restarting an instruction. The case for improved performance for reduced instruction set architecture is strong, but one could perhaps still make an argument for a CISC. A number of studies have been done, but not on machines of comparable technology and power. Further, more studies have not attempted to separate the effects of a reduced instruction set and the effects of a larger register file. The, quote, circumstantial evidence, however, is suggestive. So here we're showing two comparisons of register-register and memory-to-memory approaches. Okay, this emphasis on register-to-register operation is notable for RISC designs. Contemporary CISC machines provide such instructions, but also include memory-to-memory and mixed register / memory operations. Attempts to compare these approaches were made in the 1970s before the appearance of the RISC. So what we're showing here in figure 17.5a illustrates the approach taken. Hypothetical architectures were evaluated on program size and the number of bits of memory traffic. Results such as this one led one researcher to suggest the future architecture should contain no registers at all. One wonders what he would have thought at that time of the RISC machine once produced by Python Pyramid, which contained no less than 528 registers. What was missing from those studies was a recognition of the frequent access to a small number of local scalars, and that with a large bank of registers or an optimizing compiler, most operands could be kept in registers for long periods of time. Thus, figure 17.5b may be the fairer comparison. After the initial enthusiasm for RISC machines, there has been a growing realization that one, RISC designs may benefit from the inclusion of some CISC features, and two, CISC designs may benefit from the inclusion of some RISC features. So it's hard to find the best of both worlds, in other words. The result is that the more recent RISC designs, notably the PowerPC, so that's a little bit older now, but still an example of a RISC processor, are no longer, quote, pure RISC, and that the more recent CISC designs, and so we can be thinking about the Pentium 2 and later Pentium models do incorporate some RISC characteristics. So trying to maintain market and thinking about the end consumers, there isn't always keeping clean in either a CISC or a RISC approach. For the purpose of this comparison, the following are considered typical of a classic RISC. One, a single instruction size, and two, a size is typically 4 bytes. A small number of data address modes, typically less than 5. The parameters is difficult to pin down in the table. Register and literal modes are not counted, and different formats with different offset sizes are counted separately. Number 4, no indirect addressing that requires you to make one memory access to get the address of another operand in memory. 5, no operation that combine load and load/storage with arithmetic. For example, add from memory and add to memory. 6, no more than one memory addressed operand per instruction. 7, does not support arbitrary alignment of data for load/store operations. Maximum number of uses of the memory management unit, the MMU, for data addressing in an instruction. 9, number of bits for integer registers specifier equals to 5 or more. This means that at least 32 integer registers can be explicitly referenced at a time. And 10, the number of bits for floating point registers specifier equals to 4 or more. This means that at least 16 floating point registers can be explicitly referenced at a time. Items 1, 2, 3 are an indication of the instruction decoder complexity. Item 4 through 8 suggest the ease of or difficulty of pipelining, especially in the presence of virtual memory requirements. Items 9 and 10 are related to the ability to take good advantages of compilers. In the table that we're showing here, the first 8 processors are clearly RISC architectures. The next 5 are clearly CISC. And the last 2 are processors often thought of as RISC that are in fact have many characteristics of CISC characteristics. As we discussed in section 16.4, instruction pipelining is often used to enhance performance. Let us recognize that in the context of RISC architecture, more instructions are register to register, and an instruction cycle has the following 2 stages. I, instruction fetch, and E, execute. Perform an arithmetic logic unit operation with register input and output. So we do the fetch, execute. So keep that in mind. For the load and store operation, 3 stages are required. First, we have the instruction fetch. Then we have E, the instruct, execute, calculate memory addresses, and then we have memory, register to memory, or memory to register operation. Figure 17.6a depicts the timing of a sequence of instructions using no pipelining. Clearly, this is a wasteful process. Even very simple pipelining can substantially improve performance. Figure 17.6b shows a 2-stage pipelining scheme, which the I and E stages of 2 different instructions are performed simultaneously. The 2 stages of the pipeline are an instruction fetch stage and an execute memory stage that executes the instruction, including register to memory and memory to register operations. Thus, we see that the instruction fetch stage of the second instruction can be performed in parallel with the first part of the execute/memory stage. However, the execute/memory stage of the second instruction must be delayed until the first instruction clears the second stage of the pipeline. This scheme can yield up to twice the execution rate of a serial scheme. 2 problems prevent the maximum speedup from being achieved. First, we assume that a single port memory is used and that only 1 memory access is possible per stage. This requires the insertion of a wait state in some instruction. Second, a branch instruction interrupts the sequential flow of execution. To accommodate this with a minimum circuitry, a no-op instruction can be inserted into the instructions stream by the compiler or assembler. Pipelining can be improved further by permitting 2 memory accesses per stage. This yields a sequence shown in figure 17.6c. Now up to 3 instructions can be overlapped, and the improvement is as much as a factor of 3. Again, branch instructions cause the speedup to fall short of the maximum possible. Also note that data dependencies have an effect. If an instruction needs an operand that is altered by the preceding instruction, a delay is required. Again, this can be accomplished by a no-op. The pipeline discussed so far works best if the 3 stages are of approximately equal duration. Because the E stage usually involves an arithmetic logic unit, it may be longer. In this case, we can divide into 2 sub-stages. E1, register file read, and E2, arithmetic logic unit operation and register write. Because of the simplicity and the regularity of risk instructions set, the design of the phasing into 3 or 4 stages is easily accomplished. Figure 17.6D shows the results with a 4-stage pipeline. Up to 4 instructions at a time can be underway, and the maximum potential speedup is a factor of 4. Note again the use of no ops to account for data and branch delays. Perhaps I didn't define this, but no op means no operation. So it's basically you have an operation that you can use that means literally don't do anything when you do this command. All right, well, let's talk about optimization of pipelining. Because of the simple and regular nature of risk instruction, it's easier for hardware designers to implement a simple, fast pipeline. There are a few variations in instruction execution duration, and the pipeline can be tailored to reflect this. However, we have seen that data and branch dependencies reduce the overall execution rate. To compensate for these dependencies, code reorganization techniques have been developed. So we have delayed branch, we have delayed load, we have loop unrolling, and so these are some things that you can go ahead and pause the video if you want and go through these in more detail. So first, let us consider branching instructions. So this is the delayed branching that we were just referring to. So delayed branch is a way of increasing the efficiency of the pipeline. It makes use of a branch that does not take effect until after execution of the delay instruction, hence the term delayed. The instruction location immediately follows a branch is referenced to the delay slot. This strange procedure is illustrated in table 17.8, which we're showing here. In the column labeled normal branch, we see a normal symbolic instruction machine language program. After 122, 102 is executed, so here, the next instruction to be executed is 105. So we see a jump to regularize the pipeline, and no op is inserted after this branch. However, increased performance is achieved if the instruction at 101 and 102 are interchanged. So here we can see some examples of how we can be thinking of how to make things work better. Figure 17.7 shows the result. Figure 17.7a shows a traditional approach to pipelining. This type discussed in chapter 16. I recommend that you go back and look at figure 16.11 and 16.12. The jump instruction is fetched at time 4. At time 5, the jump instruction is executed at the same time the instruction 103, the add instruction is fetched. Because a jump occurs, which updates the program counter, the pipeline must be cleared of instructions. 103 at time 6 instruction, 105, which is the target of the jump, is loaded. Figure 17.7b shows the same pipeline handled by a typical risk organization. The timing is the same. However, because of the insertion of the no-op instruction, we do not need special circuitry to clear the pipeline. The no-op simply executes with no effect. Figure 17.7c shows the use of the delayed branch. The jump instruction is fetched at that time 2 before the add instruction, which is fetched at time 3. Note, however, that the add instruction is fetched before the execution of the jump instruction has a chance to alter the program counter. Therefore, during time 4, the add instruction is executed at the same time that the instruction 105 is fetched. Thus, the original semantics of the program are retained, but 2 fewer block cycles are required for execution. This interchange of instructions will work successfully for unconditional branches, calls, and returns. For conditional branches, this procedure can be blindly applied. If the condition that is tested for the branch can be altered by the immediate preceding instruction, then the compiler must refrain from doing this interchange and instead insert a no-op. Otherwise, the compiler can seek to insert a useful instruction after the branch. the experience both with the Berkeley RISC and the IBM 801 systems is that the majority of conditional branch instructions can be optimized by this fashion. So here we're getting in the kitchen, if you will, and seeing how things are made. And we're seeing yet again some examples of things that work to make things work better, and not necessarily the straightforward way if you would think from first blush. A similar sort of tactic called the delayed load can be used on load instructions. On load instructions, the register that is to be the target of the load is locked by the processor. The processor then continues execution of the instruction stream until it reaches an instruction requiring that register, at which point it idles until the load is complete. The compiler can rearrange instructions so that the useful work can be done while the load is in the pipeline is efficiently let me try that again. If the compiler can rearrange instructions so that the useful work can be done while the load is in the pipeline, efficiency is increased. So let's look now at loop unrolling. Another compiler technique is to improve instruction parallelism, is what's called the loop unrolling. Unrolling replicates the body of a loop some number of times, called the unrolling factor, and iterates by step U instead of step 1. Unrolling can improve performance by reducing loop overhead, increasing instruction parallelism by improving pipeline performance, and improving register data cache or TLB locality. Figure 17.8 illustrates all three of these improvements in an example. Loop overhead is cut in half because the two iterations are performed before the test and branch at the end of the loop. Instruction parallelism is increased because the second assignment can be performed while the results of the first are being stored and the loop variables are being updated. If array elements are assigned to registers, register locality will improve because AI and AI plus 1 are used twice in the loop body, reducing the number of loads per iteration from 3 to 2. As a final note, we should point out that the design of the instruction pipeline should not be carried out in isolation from other optimization techniques applied to the system. For example, we can consider that scheduling of instructions for the pipeline and the dynamic allocation of registers should be considered together to achieve the greatest efficiency. So in other words, there's a lot of tools of the trade that we are getting a chance to do a survey of, and we want to be thinking about all of those as we move forward. One of the first commercially available RISC chips was developed by MIPS Technology Incorporated. The system was inspired by an experimental system also using the names MIP, developed it at Stanford. So in this section, we'll look at the MIPS R4000. It has subsequently the same architecture and instruction set of the earlier MIPS designs, the R2000, the R3000. The most significant difference is that the R4000 used 64 rather than 32 bits for an internal and external data pass and for the addresses, registers, and the arithmetic logic unit. The use of 64 bits has a number of advantages over a 32-bit architecture. It allows a bigger address space, large enough for an operating system to map more than a terabyte of files directly into virtual memory for each access. With 1 terabyte and larger disk drives now common, the 4 gigabyte addressing space of a 32-bit machine becomes limiting. Also, the 64-bit capacity allows the R4000 to process data such as IEEE double precision floating point numbers and character strings up to 8 characters in a single action. The R4000 processor chip is partitioned into 2 sections, one containing the CPU and the other containing a coprocessor for memory management. The processor has a very simple architecture. The intent was to design a system in which the instruction execution logic was as simple as possible, leaving space available for logic to enhance performance. For example, the entire memory management unit. The processor ports 32 64-bit register. It also provides for up to 128 kilobytes of high-speed cache, half each for instructions and data. The relatively large cache, the IBM 3090, provides 128 to 256 kilobytes of cache, enables the system to keep large sets of program code and data local to the processor, offloading the main memory bus and avoiding the need for a large register file with accompanying windowing logic. Okay, as of now, what we're going to be doing is we'll be using a MIPS emulator for some of our assembly language programming processing. So some of the stuff that we're covering here will be useful to be mindful of. The emulator does have some nice tools to give you an overview and the specific assembly language commands that you can be doing it and other features. And so we'll be getting a chance to spend some time in class to go over that. So all MIPS R series instructions are encoded in a single 32-bit word format. All data operations are register to register. The only memory references are pure load / store operations. So register to register definitely is a lot faster. So that's a good thing for us to try and make sure that we utilize as much as possible. The R4000 makes no use of condition codes. If the instruction generates a condition, the corresponding flags are stored in a general purpose register. This avoids the need for special logic to deal with condition codes, as they affect the pipelining mechanisms and the reordering of instructions by the compiler. Instead, the mechanism already implemented to deal with the register value dependencies are employed. Further, conditions mapped onto the register files are subject to the same compile time optimization and allocation and reuse as other values stored in registers. As with most RISC-based machines, the MIPS uses a single 32-bit instruction length. The single instruction length simplifies instructions, fetches, and decodes. It also simplifies the interaction of the instruction fetch with the virtual memory management unit. That is, the instruction do not cross word or page boundaries. The three instruction formats shown here are what we're looking at figure 17.9, share the common formatting of opcodes and register references, simplifying instructions decodes. The effects of more complex instructions can be synthesized at compile time. So with its simplified instruction architecture, the MIPS can achieve very efficient pipelining. It is instructive to look at the evolution of the MIPS pipeline as it illustrates the evolution of RISC pipelining in general. The initial experimental RISC system and the first generation of commercial RISC processors achieved execution speed that approaches one instruction per system clock cycle. To improve on this performance, two classes of processors have evolved to offer execution of multiple instructions per clock cycle: superscalar and super pipelined architecture. In essence, a superscalar architecture replicates each of the pipeline stages so that two or more instructions at the same time of the pipeline can be processed simultaneously. A super pipelined architecture is one that makes use of more and more fine-grained pipeline stages. With more stages, more instructions can be in the pipeline at the same time, increasing parallelism. Both approaches have limitations. With superscalar pipelining, dependencies between instructions in different pipelines can slow down the system. Also, overhead logic is required to coordinate these dependencies. With super pipelining, there is overhead associated with the transferring instructions from one stage to the next. Chapter 18 is devoted to a study of the superscalar architecture. The MIPS 4000 is a good example of the RISC-based super pipeline architecture. Here we see in this figure the enhancing of the R3000 pipeline. So in this figure, we're showing the instruction pipeline of the R3000. In the R3000, the pipeline advances once per clock cycle. The MIPS compiler is able to record instructions to fill delay slots with code 70 to 90% of the time. All instructions follow the same sequence of 5 pipeline stages: the instruction phase, the source operand fetch from register file, the arithmetic logic unit operation or data operand address generation, the data memory reference, and right back into the register file. An illustration in figure 1710A shows that there is not one parallelism due to pipelining, but also parallelism within the execution of a single instruction. The 60 nanoseconds clock cycle is divided into two 30 nanosecond stages: the external instruction and the data access operations to the cache, each requiring 60 nanoseconds, as do the major internal operations, the op, the DA, and the IA. Instruction decode is a simpler instruction requiring only a single 30 nanosecond stage overlapped with register fetch in the same instruction. Calculation of an address for a branch instruction also overlaps instruction decode and register fetch, so that a branch at instruction can address the iCache access of instruction I+2. Let me say that again. Calculation of address over a branch instruction also overlaps instruction decode and register and register fetch, so that a branch at instruction I can address the iCache location of instruction I+2. Similarly, a load at instruction I fetches data that are immediately used at the op of instruction I+1, while an arithmetic unit / shift result gets passed directly into the instruction I+1 with no delay. This tight coupling between instructions makes for a highly efficient pipeline. The R4000 incorporates a number of technical advantages over the R3000. The use of more advanced technology allows the clock cycle time to be cut in half to 30 nanoseconds, and for an access time to the register file to be cut in half. In addition, there is a greater density on the chip, which enables the instructions in the data caches to be incorporated on the chip. Before looking at the final R4000 pipeline, let us consider how the R3000 pipeline can be modified to improve performance using R4000 technology. So figures 1710B shows a first step. Remember that the cycle and the figure are half as long as those in figure 1710A. Because they are not the same chip, the instructions in the data cache stages take only half as long, as they still occupy only one clock cycle. Again, because of the speed up of the register file access, register read and write still occupy only half of the clock cycle. Because the R4000 cache are on chip, the virtual to physical address transition can delay the cache access. This delay is reduced by implementing virtually index cache and going to a parallel cache access and address translation. Figure 1710C shows the optimized R3000 pipeline with this improvement. Because of the compression of events, the data cache tag check is performed separately on the next cycle after cache access. This check determines whether the data item is in the cache. So here we're showing the R3000 pipeline stages. So we show them one at a time in detail. Then each clock cycle is divided into a separate stage, denoted as Phi 1 and Phi 2. The functions performed in each stage are summarized here in table 17.9. I'm not going to go over these. You can stop the video and look over these in more detail if you would like. Okay, let's talk about the theoretical R3000 and actual R4000 super pipelining. In super pipelining systems, existing hardware is used several times per cycle by inserting pipeline registers to split up each pipe stage. Essentially, each super pipeline stage operates on a multiple of the base clock frequencies. The multiple depends on the degree of super pipelining. The R4000 technology has the speed and density to permit the super pipelining degree 2. Figure 1711A shows the optimized R3000 pipeline using the super pipelining. Note that this is essentially the same dynamic structure as shown in 1710C. Further improvements can be made for the R4000. A much larger and specialized adder was added. This makes it possible to execute arithmetic logic unit operations at twice the rate. Other improvements allow the execution of loads and stores at twice the rate. The resulting pipeline is shown in figure 1711B. So the R4000 has 8 pipeline stages, meaning that as many as 8 instructions can be in the pipeline at the same time. The pipeline advances at a rate of 2 stages per clock cycle. The 8 pipeline stages are as follows. Instruction fetch, first half. Virtual address is presented to the instruction cache in the translation look-aside buffer. Instruction fetch, second half. The instruction cache outputs the instruction and the TLB generates a physical address. Then we have the register file. The 3 activities occur in parallel. Instruction is decoded and checked, made for interlock conditions. That is, the instruction depends on the result of the preceding instruction. We have the instruction cache tag. Check is made, and then we have the operands are fetched from the register file. Okay, I found an error in the chart, so I'll pause the video and then I'm back here. So one of these was out of order, so I tried to fix that. So let's go in and continue. The next part is the instruction execute. One of 3 activities can occur. If the instruction is in a register-to-register operation, the arithmetic logic unit performs the arithmetic or logical operation. The instruction is a load or store, the data virtual address is calculated. And if the instruction is a branch, the branch target virtual address is calculated and branch conditions are checked. Next, we have the data cache first. The virtual address is presented to the data cache and TLB. Then we have the data cache second. The TLB generates a physical address, and the data cache outputs the data. Then we have the tag check. The cache tag checks are performed for loads and stores, and then write back the instruction results is written back to the register file. Okay, well, let's talk about the Spark architecture. Spark, which stands for Scalable Processor Architecture, refers to an architecture defined by Sun Microsystems. Sun developed its own Spark implementation, but also licensed the architecture to other vendors to produce Spark-compatible machines. The Spark architecture is inspired by the Berkeley RISC-V machine and instruction set and registers organization is based closely on the Berkeley RISC model. The last time I checked, there is an open Spark processor so they open source their hardware, and so that is also available. And I believe I stated this earlier, but Sun Microsystems was purchased by Oracle, and so that is the organization that contains the intellectual property that used to be with Sun. As with the Berkeley RISC, the Spark makes use of register windows. Each window gives addressability to 24 registers, and the total number of windows is implemented. The total number of implementations depends on ranges from 2 to 32 windows. Figure 1712 illustrates an implementation that supports 8 windows using a total of 136 individual registers. As the discussion of 17.2 dictated, this seems a reasonable number of windows. Physical registers 0 through 7 are global registers shared by all procedures. Each procedure sees logical registers 0 through 31. Logical registers 24 through 31, referred to as ends, are shared with the calling that is the parent procedure, and logical registers 8 through 15, referred to as outs, are shared with all calls, that is the child procedure. There are 2 portions overlap with other windows. Logical registers 16 through 23, referred to locals, are not shared and do not overlap with other windows. Again, as the discussion of section 16.1 dictates, the availability of 8 registers for parameter passing should be adequate in most cases. And so you can see table 17.4 for more information on that. So here in figure 1713 is another view of the register overlap. The calling procedure places any parameters to be passed in its out registers. The call procedure treats these same physical registers as its in registers. The processor maintains a current window pointer, the CWP, located in the processor status register, PSR, that points to the window of the current executing procedure. The window invalid mask, WIM, also in the PSR, indicates which windows are valid. With a Spark register architecture, it is usually not necessary to save and restore registers for a procedure call. The compiler is simplified because the compiler need be concerned only with allocating the local registers for a procedure in an efficient manner and need not be concerned with register allocation between procedures. Okay, let's continue thinking about synthesizing other address modes with Spark addressing modes. Most of Spark instructions reference only register operands. Register instructions have 3 operands and can be expressed in the form of RD into RS1, OPS S2. This is going to be hard for me to explain because it's not shown on this chart right now. So I'll just skip this for right now. I'd recommend that you go ahead and look in the textbook for more description of what I'm trying to talk about here. Well, I decided to stop the video for a second, and I put this one line down here so I can continue on with what I was trying to convey, and you can have an idea of what I'm talking about. So most of the Spark instruction references only most of the Spark instructions reference only register operands. Register to register instructions have 3 operands and can be expressed in the form. So RD is directed to RS1 up S2, where RD and RS1 are registered references. S2 can refer either to a register or a 13-bit immediate operand. Register 0, that is R0, is hardwired with a value 0. This is also the same in the MIPS, which we'll get a chance to be talking about in our class when we look at the emulator that we'll be using. This form is well suited to typical programs which have a high proportion of local scalars and constants. The available arithmetic logic unit operations can be grouped as follows: the integer addition with or without carry, integer subtraction with or without carry, bitwise Boolean for and, or, and exclusive or and their negations, and shift left logical right logical shift or right arithmetic. I'm sorry, let's say that again. Shift left logical, right logical, or right arithmetic. All these instructions except for the shifts can optionally set the 4 condition codes: 0, negative, overflow, and carry. Signed integers are represented in 32 32-bit 2's complement form. Only simple loads and stores instructions reference memory. There are separate load and store instructions for word. That's 32 bits, double words, half words, and bytes. For the latter two cases, there are instructions for loading these quantities as signed or unsigned numbers. Signed numbers are extended to fill only the 32-bit destination register. Unsigned numbers are padded with zeros. The only available addressing mode other than registers is a displacement mode. This is that is the effective address EA of an operand consists of a displacement from an address contained in a register. So depending on whether the second operand is immediate or a register reference, to perform a load or store, an extra stage is added to the instruction cycle. During the second stage, the memory address is calculated using the arithmetic logic unit. The load or store occurs in a third stage. This single addressing mode is quite versatile and can be used to synthesize other addressing modes as indicated in table 1710. It is instructive to compare the Spark addressing capability with that of the MIPS. The MIPS makes use of a 16-bit offset compared with a 13-bit offset on the Spark. And I made a comment on MIPS earlier, so this is another comparison. On the other hand, the MIPS does not permit an address to be constructed from the contents of two registers. As with the MIPS R4000, Spark uses a simple set of 32-bit instruction formats. See figure 1714. All instructions begin with a 2-bit opcode. For most instructions, this is extended with additional opcode bits elsewhere in the format. For the call instructions, the 30-bit immediate operand is extended with 2 0 bits to the right to form a 32-bit PC relative address in 2's complement form. Instructions are aligned on a 32-bit boundary so that the form of addressing suffices. The branch instruction includes a 4-bit condition field that corresponds to the 4 standard condition code bits so that any combination of conditions can be tested. The 22-bit PC relative address is extended with 2 0 bits on the right to form a 24-bit 2's complement relative address. An unusual feature of the branch instruction is an ANL bit. When the ANL bit is not set, the instruction after the branch is always executed, regardless of whether the branch is taken. This is the typical delay branch operation found on many RISC machines and described in section 17.5. And you can look at figure 17.7. However, when the ANL bit is set, the instruction following the branch is executed only if the branch is taken. The processor suppresses the effect of that instruction even though it is already in the pipeline. This ANL bit is useful because it makes it easier for the compiler to fill the delay slot following the conditional branch. The instruction that is the target of the branch can always be put on the delay slot because if the branch is not taken, the instruction can be annulled. The reason this technique is desirable is that the condition branches are generally taken more than half the time. The sethe instruction is a special instruction that used to form a 32-bit constant. This feature is needed to form large data constants. For example, it can be used to form a large offset for a load or store instruction. The sethe instruction sets the 22 high order bits of a register and its 22-bit immediate operand, and zeroes out the lower order 10 bits. An immediate constant of up to 13 bits can be specified in one of the general formats, and such an instruction could be used to fill the remaining 10 bits of the register. A load or store instruction can be used to achieve a direct addressing mode. To load a value from location K in memory, we could use the following Spark instructions. Once again, I'm not going to read all this. This is something that is in the textbook. So just up to that point, I'll kind of stop there. So just to finish up there, I was talking about the setting instruction set. So we have that. I refer you to the text for more details of looking through an example. And then following that, we have the floating point format. And so the floating point format is used for floating point operations. 2 source and 1 destination registers are designated. And finally, all other operations, including loads, stores, arithmetic and logical operations, use one of the last 2 formats shown in figure 17, 14. One of the formats make use of 2 source registers and a destination register, while the other uses 1 source register, 1 13-bit immediate register, and 1 destination register. So we're seeing some fixed length in the instructions, 32 bits. That's the same as what we use in the MIPS and ARMS. We have these other formats here, and I didn't really explain what the SETI format is, but you can go ahead and look up the textbook to get more details if you would like to explore that further. Okay, let's look at the pipeline organizations with buffers and pre-decoding. So this section looks at some of the enhancements to the pipeline, and this will be the last topic that we'll cover in this lecture. So enhancement to the pipeline illustrated in figure 1623 that can be used to improve performance. To begin, we merge the instruction decode and the operand fetch stages into a single ID stage, with the ID stage responsible for instruction decode and register operand fetch. This is appropriate for a RISC machine in which most operands are registers. It can also be used in CISC machines. In either case, memory operand fetching is deferred to the load/store unit, LSU. So in figure 1715, it shows the addition of the 3 enhancements: the instruction buffer, the store buffer, and the pre-decoder. All are designed to smooth out and enhance the flow of instructions through the pipeline. The instruction buffer supports the function of instruction prefetching. The objective is to prevent or at least minimize delays in issuing instructions due to L1 instruction cache misses. Without instruction prefetching, when a cache miss occurs in the L1 instruction cache, the pipeline freezes until new instructions are brought from the L2 cache into the L1 cache. To counter this, the IF stage can fetch multiple instructions to keep the instruction buffer full, so that when a miss occurs, the ID stage still has instructions to draw upon from the instruction buffer. Occasionally, when branches occur, instructions will need to be flushed from the instruction buffer, but overall performance is improved. The pre-decoder offloads some of the tasks of the instruction decoder stage to avoid the ID stage becoming a bottleneck, as previously discussed. The function of the instruction decoder includes decoding and opcode and operand fields, evaluating dependencies and hazards. As the pipeline structure becomes more complex, these functions take more time, especially for a CISC machine such as the x86 architecture. However, as we move to the superscalar architecture in the next chapter, in which multiple instructions are decoded in parallel, even RISC architectures require substantial decoding time. The objective with the pre-decoder is to perform some of the decoding ahead of the time to reduce the burden of the ID stage. The PD stage is inserted between the L2 cache and the L1 instruction cache. Because of the relatively slow L2 cache time, there is spare time here to perform the PD function. The PD may add a few bits to the instruction to designate the type of instruction and the resource required for a CISC instruction architecture. The PD may also determine an instruction length and decode instruction prefixes. Another buffer, the store buffer, improves performance on store operations. In essence, the store buffer allows a load to bypass the completion of a store to access a memory location. Thus, the load instruction can make use of a data item as soon as it's created, that is finished, and does not have to wait for the data item to be stored in the data cache that is completed. This feature is especially useful for long instructions in which data created in one iteration is used immediately in the next iteration. On loads, the LSU examines the load buffer as a look-aside buffer and extracts the data from there if available. Otherwise, it queries the data cache as normal. Figure 1715 that we're showing here illustrates the pipeline structure with an addition of the instruction buffer, the store buffer, and the predecoder to the organization shown in figure 1623. So you may want to go back and forth between these two if you want to have a comparison. Next, we will consider three more features to enhance performance: the multiple reservation stations, forwarding, and the reorder buffer. So next, we consider three more features to enhance performance: multiple reservation station, forwarding, and the record reorder buffer. The reservation station was described in section 16.5. You can look back at figure 1624 if you would like. It overcomes the bottleneck problem that the ID cannot receive a new instruction until the preceding decoder is issued. If the corresponding functional unit, that is the ALU, CTU, LSU, etc., is not available, then an ID stage stalls. The reservation station allows the ID to issue the instruction into the reservation station, which can buffer multiple instructions pending their dispatch to the appropriate functional unit. Figure 1623 shows a single reservation station that serves the FUs. The control of such an arrangement is relatively complex and is rarely used. The Pentium is an example of a system that used a single reservation station. An improvement both in performance and simplicity is the use of a dedicated reservation station for each individual FU. The process of dispatching an instruction to a functional unit proceeds in two parts. There's the issue from an ID to reservation station. Each slot in the reservation station serves the role of a virtual FU to which the ID issues an instruction. There is no stall unless all of the slots in the reservation station for a given FU are in use. That is, that the buffer is full. Then there's a dispatch from reservation station to FU. The dispatch occurs when the corresponding FU is available and all operand values are available. However, dispatch does not have to be first in, first out, but rather different priorities can be assigned to different instructions. The reservation station is also referred to as an instruction window, particularly in the superscalar literature, and we use this later term in chapter 18. For data forwarding, addresses the problem of read after write delays due to WB delays. As with the store buffer, data forwarding makes data available as soon as it is created. The forwarded data becomes input to the reservation stations going to an operand field. The record buffer supports out of order execution. Out of order execution is an approach to processing that allows instructions for high performance microprocessors to begin executing as soon as their operands are ready. Although instructions are used in order, they can proceed out of order with respect to each other. The goal of this processing is to allow the processor to avoid a class of stalls that occurs when the data needed to perform an operation is unavailable. This process is discussed in chapter 18, so we'll come back to that in the next chapter. The reorder buffer assures the instruction complete in order. The reorder buffers are discussed in Appendix G, so you can look at some of the material there if you'd like to look at that in more detail. Okay, this will be the last chart before we do our summary. So in this figure, we are looking at pipeline organization with forwarding, reorder buffer, and multiple reservation stations. So it adds all those features on multiple reservations, forwarding and buffer and record buffer to the organization that we were showing previously in figure 1715. Note that the forwarding function occurs at finish time prior to the reorder buffer and completion of the write back. So just to do a quick comparison, this is what we had in 1715. This is what we have in 1716. And so if you like, you can go ahead and pause the video and look at that in more detail. Okay, well, we covered a lot of detail here. Hopefully you're getting the big picture of what we're trying to accomplish. We're trying to get more specific in terms of what are the advantages of processors. And so for this lecture, we were looking at the pros and a little bit of the cons for the reduced instruction set computers, having everything having the same length instead of variable length for the instruction set, and looking at some of the design options. So we looked at the instruction execution characteristics, the use of large register files. We talked about the reduced instruction set architectures. We then talked about pipelining and talked about some interesting ways of how you can be looking at optimization, even flipping around some of the commands, and then making sure that we don't do things out of order at the end, but at least we can start things in parallel. So we have, we looked at the MIPS R4000, we looked at the Spark architecture that was developed by Sun Microsystems, and then we looked at processor organization and looked at various ways of pipelining, and then finally thought about CISC, RISC, and contemporary systems as we finished up the lecture. All right, well, thank you very much. That'll finish things for here.